quick demonstration of finding and changing correlated residuals in AMOS. So this is the model that we left off with. It's the memory and reasoning model that has a correlation, a fit of chi-square 100.8. So how do we find the correlated uniqueness? Well, let's take a look here at the ledger and let's see if we can find the uniquenesses. So over here under Modification Indices, what you see here in the top is a table of covariances, and these show us a bunch of modification indices. Remember that a modification index is the size that we think chi-square will go down if we free up this parameter. Now you'll notice 4 of these parameters are correlations between a uniqueness and a factor. E3 and E2 correlated with reasoning and memory. These are not good to free up. One typically never wants to free up a uniqueness with a factor correlation. It damages the internal consistency and interpretability of the factor. So when people free up correlated uniquenesses, they usually do so between correlated uniquenesses. So we see 4 of them in this table, between E3 and E6, E3 and E5, E1 and E3, and E1 and E2. The highest of these correlated uniquenesses is between E1 and E3 with a value of 23.42. Now that's a very interesting uniqueness to us because it's between 2 residuals on the same factor. They're both memory. So freeing them up also in some ways almost seems to add internal consistency to the memory factor. When you have a choice, you always pick the largest within factor correlated uniqueness. Now your homework says just free up the largest correlated uniqueness, it doesn't matter what factor. And that's just for the purposes of the homework. But in real life, when you free up correlated uniquenesses, you usually try to do so between 2 uniquenesses within the same factor. E1 and E3 fits that bill, and the program tells us if we free up that correlated uniqueness, we may see a chi-square improvement of up to 23 points. So let's go ahead and do it. I'll close the output window, pick the arc tool, and draw a correlated uniqueness between E1 and E3. Now analyze, calculate estimates to rerun the model. And what I hope you can see here is that already the model has a chi-square of 45.3, a reduction in fact of 55 points, more than the modification index led us to believe would happen. Using the ledger tool to look at the output, I'll click here on Notes for Model, which would tell me if there were any admissibility problem. There aren't. So let's take a look at the estimates. A quick eyeball here tells me that none of the estimates look illegal. I don't have what seem to be weirdly high values or negative variances. We'll talk about that more in class. And down here in the covariance section, I see that the freely estimated correlation between E1 and E3 is significant, 3 stars. I also see that the bivariate correlation between E1 and E3 is estimated at minus 0.38. So what that means is above and beyond, in this case, HVLT and reasoning's associations with the memory factor at the factor loading level, these 2 indicators have an additional residual association that's negative. People who do better on list memory seem to do more poorly on story recall. That actually, there's probably some sense to that. That's a small residual association that exists above and beyond the factor. By finding and freeing up this uniqueness, we greatly improve the fit of the model. If we look at the fit statistics, the chi-square to degree of freedom ratio is now 6 instead of the 12 that it was before, and all of these goodness of fit statistics are now very close to 1, often having values in the 0.98 to 0.99 range. Again, we'll talk about this more in class, but this is just a quick demonstration of how to find and free up a correlated residual.